Hi, we are going to discuss briefly about thermodynamics. The first topic to be discussed here is specific heat capacity. When you give some quantity of heat energy to a substance, say dq is the energy given to the substance, then this quantity of heat is a product of three factors. The mass of the body in which you are giving the heat energy, specific heat capacity C of that particular body. It varies for solids, for liquids, for gases, it varies. And the difference in temperature. Difference in temperature means before giving the heat energy, what is the temperature of the body? After giving the temperature, what is the temperature of the body? After giving the heat, what is the temperature? Final temperature. That final minus initial will be dT. So this is the quantity of heat supplied by the system by kinetic theory of gases. C is called specific heat capacity. Now I want to define C. So C is equal to dq by m into dt. When you say m is equal to 1 kilogram and difference in temperature dt as 1 degree Celsius, then I can write specific heat capacity is numerically equal to the quantity of heat supplied. So you can define specific capacity as specific capacity of the body or a substance is numerically equal to the quantity of heat supplied for a body of unit mass having unit change in temperature. Unit change in temperature means 1 degree Celsius. Sir, how can I convert as 1 kilogram body? How can I convert for 1 degree Celsius difference in temperature? Let the mass be any value. You calculate for 1 kilogram. The temperature difference we don't know. Let it be 10 degree, 25.5 degree, 80 degree, 90 degree, anything. You calculate for 1 degree Celsius. 50 degree you calculate means divide by 50 means you will get for 1 degree. So unit of C, quantity of heat, joules. Mass is expressed in kilogram, temperature in Kelvin. Degree Celsius you are calculating, convert into Kelvin. 0 degree Celsius is 273 Kelvin. So unit of specific heat capacity is joules per kilogram per Kelvin. When you say specific heat capacity at constant pressure or specific heat capacity at constant volume, you can write Cp Cv. Same definition. You can put Cp, but mass here is 1 mole of a gas. It is not 1 kilogram, it is 1 mole of a gas. So, specific capacity at constant pressure is numerically equal to the quantity of heat supplied for a body of mass 1 mole or 1 mole of a substance having unit increase in temperature with unit rise in temperature. Unit rise means 1 Kelvin. 1 degree itself is difficult. You calculate for 1 degree, divide by 273, you can convert into Kelvin. Same definition at constant volume. Molar specific heat capacity at constant pressure. Molar specific heat capacity at constant volume. or specific capacity at constant pressure, constant volume. Basic formula dq is equal to mass into specific heat into difference in temperature. Okay, fine. Using Mayer's relation, we can calculate the relation between Cp and Cv. Cp minus Cv is equal to R. Specific capacity at constant pressure, specific capacity at constant volume is equal to universal gas constant R. Cp value only greater always. So you can calculate specific capacity for different gas molecules, monatomic, diatomic, triatomic gas molecule. You can calculate Cp, Cv, both values. Once you know Cp value means Cv value you can calculate using the relation. Or either way, if you know Cv, Cp can be calculated. Monatomic gas molecule, diatomic gas molecule, triatomic gas molecule. First law of thermodynamics. Of course, we have zeroth law also. Zeroth law of thermodynamics. A and B are in thermal equilibrium with one another. B and C are in thermal equilibrium with one another. Any system which has got pressure, volume, temperature, we call it as thermodynamic system. You take a container with a gas with a frictionless piston. Pressure of the gas, volume of the gas, temperature of the gas. That is called thermodynamic system. Thermal equilibrium means the particular system is in thermal equilibrium. That is the change in pressure, change in volume, change in temperature with respect to the surrounding. You are going to calculate. It is going to be in equilibrium with the surrounding. Thermal equilibrium. One system having pressure P1, B1, T1 temperature. Another system P2, V2, T2. When you combine these two, you will have common pressure, common volume, common temperature. Now you can say these two are in thermal equilibrium with one another. So A and B, three systems we have. A and B are in thermal equilibrium with one another. A and C are in thermal equilibrium with one another. Then definitely B and C should be in thermal equilibrium with each other. 100%. A1, P1, V1, T1, P2, V2, T2, P3, V3, T2. These two are in thermal equilibrium. These two are in thermal equilibrium. A and C. No, sir. A and B are in thermal equilibrium. B and C are in thermal equilibrium. Then definitely A and C should be in thermal equilibrium. Either way. Okay. When you consider a container with a frictionless piston as having some gas inside, you are compressing the gas, you are expanding the piston. When you supply external heat energy, the gas pushes the piston upwards. Work done by the gas. When you compress it, work done on the gas. So change in pressure, change in volume, change in temperature. This is thermodynamic process. So the energy what you are giving is dq. That is sum of two factors. One is change in internal energy of the system. Another is work done by the system. dq is equal to du plus dw. dq is equal to du plus dw. du is change in internal energy. Gas molecules are moving, so kinetic energy. Gas molecules are positioning somewhere, so potential energy. Work done, piston moving upwards, downwards. Work done by the system. This is called first law of thermodynamics. You have one process on a cyclic process. Cyclic process means system will come back to the normal after doing some work. That is called cyclic process. So in cyclic process, change in internal energy is zero. UF minus UI, final internal energy minus initial internal energy only du. Cyclic process, the system comes back to normal. So what is the meaning? du becomes zero because UF and UI are equal. So I can write dq is equal to dw for cyclic process. This is first law of thermodynamics. Okay. Next one. Second law, Clausius statement. We have got various forms of second law of thermodynamics. Clausius statement. Kelvin statement. Kelvin Planck statement. General form of second law of thermodynamics. Heat can be converted into work, or when you do some work, heat energy is produced, vice versa. These two can happen only one body at lower temperature, another body at higher temperature are available. Then only can convert this form. Heat energy can be transformed from one form to the other. That is a different thing. That is conservation. So here, when you say the transformation, or when you do some work, heat energy is produced. As long as one body at lower temperature, another body at a higher temperature is available. Or without supplying any external energy, you cannot cool a system. Or you cannot extract heat energy from the system by cooling it cooler than the surroundings. Surrounding temperature is 30 degree. Body temperature is 20 degree. Surrounding 30 degree. This is body temperature. So the body temperature is less than that of surrounding. So I cannot extract heat energy from the body. This is another form of second law of thermodynamics. Okay, fine. From lower level to higher level, water should be shifted. Higher level to lower level, automatically the water will flow. Whereas lower level to higher level means you have to pump the water. You need a motor. So higher temperature, lower temperature, automatically will come. Low to high means you have to provide some external energy. This is some form of second law of thermodynamics. Okay. Isothermal process. Isothermal process. Adiabatic process. These two things you're going to see in thermodynamics. We have isochoric process, we have isobaric process and all. Only these two we will focus. Isothermal process. Pressure and volume of the system changes, but the temperature remains constant. That is called isothermal process. PV is equal to constant. Pressure and volume changes, but temperature remains constant. Okay. Of course, here frictionless piston, some gas is present, surrounding is non-conductive. When you compress the piston slowly or allow the piston to expand slowly, surrounding temperature cannot come into the system. The temperature of the system decreases, increases and all will not happen because system is very, very slow. Very slow process. So temperature remains constant. Pressure of the system changes, volume of the system changes, but temperature remains constant. This is called isothermal process. Adiabatic process means process must be quick. Surrounding should be perfectly conducting. The container is surrounding with the perfect conducting with the walls of the container. So when you compress the gas forcibly, the temperature increases. The temperature will go to the surrounding. But before that, the temperature of the system increases. So temperature is not a constant. Temperature is not a constant means it is called adiabatic. Nothing can enter. Before that, the system gone. The equation for that is PV power gamma is equal to constant, where gamma is ratio of specific heat capacity of gases. Gamma is equal to Cp by Cv. Nearly the value is 1.42. Near value. Because Cp is always greater than Cv. Cp by Cv, nearest value 1.4. Correct? This is adiabatic process. What is called work done by the thermodynamic system, sir? What is called work done in thermodynamic system? Work done in thermodynamic system. Work done is force into displacement. Pressure into area into displacement. Area into displacement is volume. So dW is equal to P into dV. Is a basic formula for work done in thermodynamic process. Total work done means we have to integrate. W is equal to integral P dV. Graphically only we will represent pressure in y-axis, volume in x-axis. Now you are doing work done due to isothermal expansion. Expansion means volume increases, pressure decreases. So, like this, you can see the arrow mark. Expansion. Compression, sir. Compression means volume decreases. X-axis volume, y-axis pressure you are considering. So, arrow is here. This is initial volume. So, pressure from this point to this point increases, volume decreases for compression. Correct? No? So this is the basic information in thermodynamic system. Carnot engine. Carnot engine is nothing but a heat engine. You are giving some energy to the system. It is doing some work. Some part of energy is rejected to the sink. By taking some energy, it is doing some work. While doing the work, it is rejecting some heat energy. That is called the basic principle of heat energy, heat engine of the system. Carnot engine, basically a heat engine. You have a source giving very high temperature, and you have a sink producing very low temperature, and you have a working substance, frictionless piston with a gas. Carnot engine, overall principle only are going to see, not in detail, because the big concept. Overall view we will see. Keep the working substance with the gas on the source. Isothermal expansion, stage 1. Second stage, adiabatic expansion. Keep it on the sink. First one, you are keeping the working substance on the source. Second, keeping the working substance on the sink and allow it to expand adiabatically. The word isothermally means temperature constant. Adiabatically means temperature changes. Expansion, so temperature decreases. Third, again you keep the working substance on the source. Isothermal compression. And finally, again you keep it on the sink and compress it. The extra heat energy will go to the sink. So it is a cyclic process. Pressure, volume. The nature of the graph will be like this. First stage, second, third, fourth. So efficiency of Carnot engine is work done by the system divided by heat energy taken from the source. Q1 amount of energy you have taken. Q2 amount of energy you have rejected. Then what is the work done? Q1 minus Q2 by Q1. So I can write 1 minus Q2 by Q1. We can prove heat energy is directly proportional to temperature. So efficiency will be 1 minus T2 by T1. T2 temperature of the sink, lower temperature. T1 temperature of the source, high temperature. Any heat engine or anything you take, 100% efficiency is not possible. So a Carnot engine also 100% efficiency is impossible. How, sir? If you take eta is equal to 1, that is called 100%. When eta will become 1, T2 can be 0 or T1 can be infinity. T2 is the temperature of the sink, 0 Kelvin. Kinetic theory of gases, 0 Kelvin is impossible. So you will never get T2 can be 0 Kelvin. First. Second one, source temperature T1. What is the meaning? Source temperature T1. T1 is infinity, means eta can be 1. All temperatures are measurable. Even sun temperature itself 14 million Kelvin, measurable. So infinite temperature is not possible. So T2 cannot be 0 or T1 cannot be infinity. Therefore, efficiency of Carnot engine will never be 100%. It is always less than 100%. Okay, Amma? So this is the basic information regarding the Carnot engine. So we have discussed the basic factors of thermodynamics. Okay. Thank you. We'll continue.